A very good morning, afternoon, and evening to all of our attendees and speakers. I know that some of you will be joining us from around the world, so thank you for joining us here today for an event which marks the final in a series this week to mark WTUN for UNESCO World Engineering Day. Very excited about today's programme, having convened 9 expert speakers from across the WTUN member universities and beyond to speak on the topic Theory into Practice, Addressing the Water, Energy, Health, Environment, WHE Nexus. But without further ado, I would like to introduce our host and chair, Professor Iqbal, who will proceed with today's session. Thank you very much, Professor.
Good morning, everyone. Thank you for joining us in very short notice. So I'll not take my time. I'll share my screen and I'll just have some introductory presentation, just very short, and then we'll start the session. So our first speaker is supposed to be Professor Dominic Fu. He has not joined us yet, and we'll start with the next speaker, but let me have my introductory slides with you. So can you see my screen?
Yeah, sure.
Okay, thank you. So today's session is about theory into practice, addressing the water, energy, health, environment nexus. See if I can move. So let me just set the scene for WEHE landscape and the way forward. And so if you look at the United Nations Sustainable Development Goals, there are 17 of them, and the water, sanitation, and health, they are linked to USD Goals 3 and 6. So clean USD Goals 3 and 6 relates to clean water, decent sanitation, and good health for all. So where are we in that respect? So if we look at the global picture, 10% of the world population do not have clean water close to home, and people walk miles to get fresh water. And globally, about 2 billion people, they drink water which is contaminated with fishes, and of course, resulting in over 500,000 deaths, according to UN report. Also, the tens of thousands of women and girls are forced into sex for a few liters of water, and that is happening in Kenya. About a month ago, I signed a petition to the Kenyan government to stop these vendors, who sells a couple of liters of water in exchange of sex. And that has been confirmed recently in a symposium which I chaired in Jordan, and there are Kenyan participants who are there, and they confirmed that is happening. So almost about 1.7 billion people do not have decent toilet of their own. And as you can see, people go outside for attending nature school. The picture right at the bottom right, you can see that the ladies going in the dark, early in the morning or late in the evening to nearby jungle to attend the nature school. And that is based on the true story in India. And the film name is Toilet, a Love Story. If you have not seen it, you watch it, you will see the real picture, what is happening around the world around sanitation. They don't have the private toilet at home, they have to go outside. And it's a very nice love story around toilet, and it is based on true story. If you look at the water and economic growth, how it is linked to UN SDGs to 6 and 8, 3 out of 4 jobs that make up the global workforce are either heavily or moderately dependent on water. And water shortages and problem access to water and sanitation would actually limit economic growth and job creation. And that is based on the United Nations report, which you can see for yourself. And also recently, 2 years ago, there was a paper published in Applied Energy talking about the crisis between the water scarcity and economic development along the US-Mexico border. And it's a very interesting paper to read. If we look at the UN SDGs 267, which is linked to water, food, and energy, the water we have got, almost 80% water goes into agriculture. And that is the picture in many parts of the world. And of course, the West use less water for agriculture, but in many parts of the world, that is the case. And a lot of us talk about a biofuel and et cetera, even to produce 1 liter of biofuel would require 1,000 to 4,000 liters of water. And again, our food habit, if I put a list here, which is published several years ago by Institution of Mechanical Engineers. It's a long list, but I have cut down to a short one. I'm sure you will find your food here and you will be able to appreciate how much water goes into that processing. For example, 1 kilogram of chocolate or 1 kilogram of beef, 1 kilogram of rice, pasta, etc., down to even 1 egg, which requires about 196 liters of water. The reason I put egg right at the bottom, because I love eggs. I cannot have a day without egg. And the same goes true with my wife as well. So we both like eggs, and probably that's the reason probably we have been together for around 40 years now. So I have to put that, and I have to remind every morning, the amount of water goes in processing 1 egg. And then again, we have got a choice, having the shower or a bath. If we have got a bath and a luxury bath, that will consume 190 liters of water every time we have a bath. But a 10-minute shower would again require 90 liters of water. If we can cut down our shower every day by 5 minutes, you can think about then how much water we can save for the planet. Then, wastewater linked to health. As you can see here, the 2 pictures here, one at the top is from Bangladesh. The lady is collecting water from the river. And the river bank is surrounded by a lot of industries here polluting the river water. And right at the bottom, the picture from India, most recent one, again, the very similar picture. And as the world population grows, of course, we use more water and our industries use more water, and we end up with a huge amount of wastewater. And again, 300 million tons of synthetic compounds are disposed annually into our river stream. And in 2009, about 564 toxic chemicals were identified, but now it has gone quite a high number. And still there are pollutants we cannot even measure, we cannot even trace them, and which is affecting our health. I think the most recently I was looking at that all of us to some extent have got microplastics in our body. I think whether it was the last night's news or today. So that is the situation. The microplastic we don't see in the water stream, but it is going and damaging our health. So the net effect of water pollution is impacting marine life, human health, and many others. And we have got a talk this morning from Dr. Farshid Sefat, who will talk about the impact of water into health and the remedies for that. So if we look at where we are, the population is growing, the water demand is growing, with that energy demand is growing, with that we are producing wastewater also that is growing, and our health problem is growing. So we have to look at what water resources we have got. We have to look at what energy resources we have got. We have to look at what technical solutions are. The question is, are this enough? We have to remember that annually the freshwater demand is increasing by 64 billion cubic meters a year, while world population is growing by roughly 80 million each year. So, of course, when you look at the water resources, the answer is no. We are surrounded by sea, mostly saline water, and of course, the huge amount of wastewater we have got. And then, of course, it requires technological solution, as well as there are other associated problems with that. And I'll talk to you briefly about it. So what about the surface water level, what we have? Is it enough? Is it, can I guarantee that? No. The climate change, the environmental impact has got a big effect on the surface water we have got. In 22, Spain's surface water level went down to 40% lower. And in Italy, 70% of agriculture depends on River Po, and the level went down. It affected the agricultural activities massively, and Italy declared the state of emergency surrounding River Po. And that happened in Germany as well. We are in Europe, serious disruption in supply chain. When the supply chain is disrupted, we know what impact that will have, because we have seen that during pandemic, that if supply chain is broken, then a lot of things we want to have, we will not have it. And that is in Europe. But the same thing is happening in Brazil, Amazon River, and many other parts of the world, that climate is actually impacting the level of water we have got at the surface water. If we look at the UN Sustainable Development Goals 6 and 16, and that is related to water, war, and peace. So you can see when we do not have the fresh water, of course, the war takes place, the confrontation takes place. And in India in 2009, on the 25th of May, several people died because they were queuing up for fresh water. And of course, there was not enough fresh water. So they were struggling to get it, and they died for water. And also we have to appreciate that 220 river basins globally are shared. And this is a political problem to be resolved between countries. It's not that the water is not there. Water is there, but then again, because of the political issues, of course, somebody upstream is polluting the water, and then somebody downstream, they have to clean the water, and who will be accountable for this sort of activity? So it's very, very important. Also, the link between environmental problems and conflict due to extreme water shortages in the Middle East, we are seeing it, and it is increasing more and more. I have just looked at one of the research proposals from WED, and I was really, really shocked to see the level of sea pollution they have got around WED city, and which is, of course, impacting the production of water and the use of water in chemical industries or other process industries. So technical solution to make fresh water cannot resolve this problem. What about the wastewater and use of the wastewater for our use? The yuck factor is a major problem for people to accept the reclaimed wastewater to use it. And I have seen that in Singapore. I have seen that in many places in the world. Even the Londoners think it's too much to drink, treated wastewater. So that's where we are, because it's a social problem, social awareness of the problem, because it's a trust between the government and the people that the treated wastewater is still safe to drink. Having said that, this is my last slide, hopefully. So when you look at the water resources, land resources, energy resources, of course, that if they are not properly managed, then you end up with the energy security, food security, water security problem. And all these problems, if we have got, then that will lead to our health problem. So they are all interlinked, and I believe that this workshop will give us food for thoughts, how to tackle this problem, what are the issues, and what we can do together to resolve such issues. So I will end with that one. I'll unshare the screen and then see if we have got Professor Dominic Fu here. Is Professor Dominic Fu here? Right, probably he's not. So I will invite our next speaker. So I will invite Dr. Pedro Arcelus-Arrillaga from the University of Bradford to make his presentation. Can I please remind you that you have got only 10 minutes, and I will give you a reminder after, when the 2 minutes are left, and then you need to stop because we have got a very limited time. And after Professor Dr. Pedro Arcelus-Arrillaga's presentation, Professor Raed Abd-Alhameed will present. Thank you.
Excellent. Thank you, Professor Mujtaba. I will try to share my screen. Please let me know if it looks okay.
Yeah, that's fine. We can see it.
So I will put it presentation mode. Still you can see the presentation, or you see the double screen?
We see double screen, but it should be fine, I believe.
Okay. This shouldn't be the case, but well, I should start, no? Just for...
Yes, please.
Excellent. Well, thank you very much for letting me speak to you about my research on the solar-heated hydrothermal liquefaction of organic waste. I think it's a very timely topic for this workshop, as we are studying the reuse of organic waste to produce fuel, so considering waste as a feedstock. My research interest land in the hydrothermal treatment of different feedstocks, one of them being organic waste. So the way we do it is we use water as reaction medium at high temperatures and pressures to convert it into low carbon fuels and also value-added chemicals that are very valuable for pharmaceutical or food industries. I will drive you quickly through my research into this area with the interest of reaching the part that we are designing solar heated reactors in order to actually perform this process. So as Professor Mujtaba was already introducing, I'm not going to stop much here, but the increase in population will result in an increase of the consumption of energy. And the increase of consumption of energy will end up being in higher CO2 emissions to the atmosphere and in a difficult, and we will find ourselves in a difficult position to actually cover our energy needs. So it is expected that by the year 2050, we need to increase the participation of biofuels for the energy market in around 90%. And there are the feedstocks there, but so we are not producing enough. So developing technologies to actually achieve in producing biofuels is very important in order to cover these energy needs. So definitely we have a big challenge there. And that's the challenge that I'm exploring with my research collaborators. Biomass and municipal waste is a problem in itself. We are producing tons and tons of waste every day. And the good thing is that we can use this waste in order to transform it into value-added products. There are many challenges in processing biomass and municipal waste to produce fuels. One of them being the high water contents in these feedstocks that actually makes it really energy intensive to process them through traditional routes. And also the low density in terms of energy that we can find in biomass. So biomass is a complex, has a complex chemical structure. It's mainly composed cellulose, hemicellulose, lignin, and other organic compounds. And we need to be very efficient when we are processing these types of feedstock. So as I was telling you, traditional processing methods like pyrolysis or gasification, in some occasions, depending on the process, require dry biomass. The same happens with combustion. So if we have to pre-treat these feedstocks, that means that we are going to invest lots of energy, perhaps even more than the energy that we will receive from the fuel. In this respect, hydrothermal liquefaction is a good way of doing it because we can avert and prevent this energy-intensive pre-drying stage and process with high efficiency biomass to produce biofuels. Apart from that, water is a fantastic reaction medium, that has properties that can change with very minor changes in process conditions. So with small changes in pressures and temperatures, we can actually tune the process and make it selective to certain particular products of interest. So that is also something that is very important. And finally, water. Why? Water is a green, non-toxic, and in some way we can consider abundant reaction medium that we can use, and then we can treat again to reuse for processing biomass and organic waste. The interesting thing that I was telling you about the process conditions is that with changes, we can change the process completely. We can operate in hydrothermal conditions to favor the formation of gas, for example. So we can have hydrothermal gasification, or we can decrease temperature and pressure and actually prioritize selectivity to solid products. So we can produce hydrochars, we can liquefy, depending on the process conditions that we set. The range of products that we can obtain is very big. So I will talk to you more about my research in liquefaction because I'm currently interested in producing liquid fuels. So this is a research that I performed with some colleagues in Mexico and also some colleagues in Spain. And we studied the hydrothermal liquefaction of residual coffee pulp. So we have this agriculture waste. We process it in hydrothermal conditions, as you can see there, ranging between 200 and 320 degrees Celsius at high pressures of 120, 180 bars in a batch reactor. I'm not going to go through the table because that would be a lot of time, but what I can tell you is that you can see what you see in the red square. We managed to increase the energy content in the biomass by almost the double. And we explored high temperature, high pressures, or low temperatures, low pressures, and we can see that it has an important impact in the final product. Also, we achieved high yields up to 25% to bio-oil, which is a very good result. The types of products that we got is we have gases that are rich in hydrogen. We also have aqueous products that are rich in block chemicals and fine chemicals that we can process and separate, purify and sell it at a good price. We also have the hydrochars that we can use as fuel and the bio-oil that can be used for many, many things. As you can see there, the energy content of bio-oil and biochar is quite high. We achieved close to 30 megajoules per kilogram, which is already good, but is not yet comparable to what we have in crude oil. So further improvement of the quality of the bio-oil would be needed, and we are currently exploring it as well. The hydrothermal liquefaction process is an energy-intensive process. We need to reach high temperatures and high pressures. Sometimes we can spend even more energy that we may be improving in terms of the original feedstock. So our current effort is to incorporate solar heating technology to the hydrothermal liquefaction process. So in collaboration with the Institute of Renewable Energy in Mexico and the Center for Investigaciones Ópticas in Aguascalientes in Mexico as well, we have designed and commissioned a first prototype that you can see there in the picture at the right, bottom right, to actually heat the reactor with solar heating in a solar oven with excellent results that I'm going to show in a second. So these are the pictures of the solar oven that we are using for these tests. And we have a very thick wall reactor because this is the first prototype we were testing. We have the solar oven that can reach temperatures as high of 1000, but it has very good control of the temperature, so we can manage to control temperature in the window between 200 and 400 Celsius. That is the hydrothermal liquefaction
2 minutes
range.
left.
Perfect, yeah, I'm almost there. And as you can see here in the graph that we have is the first preliminary results that we talk of, that we get on the different temperatures inside of the reactor. One of the main challenges is the temperature gradients that we have, because we have to actually direct the solar heating to a specific focal point. We are improving the design of the reactor to try to reduce these temperature gradients inside of the reactor. But what you can see is that the reaction temperature in the bulk of the liquid reaches some window of steady state. So we managed to keep the temperature constant and to actually process the biomass. Here you can see results with agave bagasse. That was the biomass that we used for hydrothermal liquefaction with solar heating. And we achieved very good yields of around 25–28% that are comparable to the yields that we got with conventional heating, and bio-oil qualities that actually achieve the same, more or less the same quality and energy content that the one that you will actually obtain through conventional heating, which is the result that we were looking for. Just to be quick and to talk about the main conclusions of this solar-heated hydrothermal research, the first conclusion is that biomass and organic waste are feedstocks with great potential for biofuel production. Second one, hydrothermal liquefaction is a very effective technology for this processing of biomass, as we don't require an energy-intensive pre-drying stage, and the water properties are very good for the chemical reactions that we are promoting. Then the solar heating prototype, the first one that we achieved, that is a batch, achieved the yields of bio-oil that we were previously obtaining through conventional heating, and the energy content on the final fuel is also similar. And just to conclude, currently we are working on a prototype to make this process continuous. So we will have a continuous solar heated prototype soon that we are going to test, because the aim is to increase the technology readiness level to bring it to actually higher TRLs. And with that, I just want to thank my collaborators in this solar hydrothermal research in the Institute of Renewable Energy and the Centros de Investigaciones Ópticas, especially the doctors mentioned in the slide. And I don't know if we will have questions now or later, but I will be here to answer any questions. Thank you.
Thank you. We will not have any question now, because we've got short of time right at the end. As a panelist, if there are questions, we'll be able to answer. I'll invite now Professor Raed Abd-Alhameed and then Dr. Cuong now, because he has to go for his teaching. Yes, Professor Raed Abd-Alhameed, please.
Thank you, Iqbal. It seems to me I have a... Do you hear me now?
Yeah, we can hear you. Yeah.
Okay, very good.
You want to share your screen?
Sorry, yeah.
You want to share your screen or?
Yeah, sure. I just trying, because I got a problem with that one.
Yes, we can see your last slide.
Oh, thank you very much. I will make it fast as well.
Yeah, because you've got 10 minutes exactly, and give you a reminder before 2 minutes. Thank you.
Yeah, thank you very much. Okay, everyone. Usually I'm going to talk about the real-time monitoring of femur fractures with an AI-enhanced RF sensors. Really, this one is a bigger project as well. The people with me as well, I wish just to acknowledge them, is John Buckley, Mariam Hardy, Rami, and there are 3 PhD students as well on the project. So this is just to give you a brief idea, and including as well, we are sharing this with 5 European countries. Of course, this one is, as I said, is supported by the EPCRC and as well Horizon 101, 131, 501. Usually, I'm sorry about this. I got flu for the last week. Never mind. I think the project is, we are trying really to provide some RF sensor to get the signals as well, and to apply AI to find to a way really to assessing, for example, the fracture healing within the patients. In general, we have this project, I mean, it just to eliminate a little pressure as well on MRI, X-ray, that cost too much money as well for the NHS. We are trying as well to build up on the RF and AI and generate some data, which I'm going to show you some values and some data, and how we are going to gather some information as well from medical doctor to identify the work we are trying really to do. In very simple, we are not only we are going to take the data, we need just to make it more portable and flexible as well, on the mounted on the human tissues, including as well, we need just to transfer it through, for example, RF signals to the cloud to make some meaning and analysis the data itself. Other thing as well, as you know, when we are going to establish the sensors on the human peer, we need as well to have automatic or adaptive sensor calibrations that can enhance the accuracy and the reality of the data we are trying really to collect from the patient themselves. Again, as well, not only we are going to integrate the sensor on the legs or on hands or any other type of position in the human body, but we are trying as well to enhance another type of sensor to give us more accurate predictions and decisions to make to the patients. We need as well to secure the data transmission as patient ethical of using these data. The other thing as well, all the process will be dealt in a real-time monitoring process where the data can be collected and to be analyzed. AI data is very important really for AI, so we need to work the machine learning and deep learning as well with these type of data. Today, I'm just give you simple examples on simple data in RF, and then how we are going to take these data to enhance, for example, patient care in terms of tell the patient don't move your leg or don't move or don't do any exercise training. We need just to enhance as well some information to the medical doctor or nurse to give them more picture about the data. And that's why clinical decision making is very important really for us. That will be integrate the RF sensors, plus as well the sensors we are going to integrate it within the movement of the patients. I will give you some kind of a simple results we are trying really to publish as well and work with. You can see it as well from here, how the bone, when the bone fracture is happening, and then when it is clear. You can see the hematoma as well generated, including the spongy bone developed as well, and woven bone, till the bone is healing on the right-hand side as well. And there. The system we generate here in Bradford is multi-sensor systems that can collect the data through inexpensive as well network analyzer. As you know, we are trying as well to put a lower frequency to put the this network analyzer very easy and can be handled as well on the patient at homes. We are trying really to do the system either using monostatic or bistatic radars. And this is very important really for us. Monostatic, it means we are transmitting, receiving the signal on the same sensors. And the signal, as you see it from here, is wide spectrum signals. It can goes from 4 to 8 gigahertz or from 1 to 3 gigahertz, which we are trying as well to improve for lower frequency and to enhance, for example, the accuracy as well for it. Here as well, it can show you the spectrum and the signals. And this one is the second generation signals that enhance, for example, the data we are collecting from transmitting the signal through these sensors. Bistatic is exactly the same, is we are transmitting and receiving from the other end. And this is a simple examples. You can see as well the sensor and the cross sections of, for example, of the leg or femur, and is a simple model as well. We can move the bone everywhere in the area, or we can generate different sizes as well of sizes of volume of that leg, and then we can generate, for example, type of fracture. Fracture, it means we need to generate a hematoma, as you can see it from there on the right-hand side. And then we can take the model into a software as well. And usually nowadays we are trying as well to do a very big project, a lab project as well, a lab experiment with Dr. Peter Twig and John Buckley and so many people as well in biomedical, really to generate the bone and the
2 minutes, right?
2 minutes?
2 minutes, yeah.
Oh, thank you very much. Yes, and this is to give you a clear picture how the signal we can compare it. This is different as well of type of the fractures we are going to see, and you can see as well the signals we are providing it has some meaning on the AI as well. And then what we have generate from, let me just skip some of the sensors. We can show you as well how we are trying as well to view the fractures in terms of RF sensors. And you can see as well when we fractures is with different type of distances and type of hematoma generated from the space of that fractures. And we are capable as well to view the fractures in even within 2 millimeter size of that. And thus we generate the deep learning, machine learning with deep learning as well, is to enhance our modifications of the data. So we take the bone thickness, bone position, muscles, fat thickness, hematoma size, and number of sensors. And we generate, for example, a very big, massive data that work on monostatic and bistatic data. And you can see as well, the accuracy we can get with the 4 sensors is around 96.8, and within 6 sensors as well, within 99.2. We are sharing this information with the medical doctors, and hopefully we are trying really to build up the experiment with our biomedical people in Bradford University, and to enhance as well the type of measurement to agree very well with the medical doctor. Thank you very much, and sorry for taking too much. Thank you, Iqbal.
Thank you very much, Professor Raed Abd-Alhameed. I'd like to invite now Professor Neagu, and then Dr. Cuong will do after that. Thank you. Professor Neagu?
Yes, joining in. Okay. Thank you very much.
So you have got 10 minutes. I will remind you just before 2 minutes.
Indeed. Let me just find the show screen thing. I'll be quite fast for a number of reasons. The important one is that I have far more slides than the number of minutes allowed, but I'll kind of swim through them. Hopefully you can see now my screen. Can you? Not very sure. It says for me that the screen is sharing, but I'm not very sure if that's the case. Would you please just confirm that you can see my screen?
We can see it now. We can see it now. Yeah.
Thank you very much. Okay, so I'll try to share if you can see this way, simply because I wanted to see that I am practically browsing through the slides. The work is a little bit larger and bigger than one can count, because the subject of sustainable and responsible AI and its alignment with the United Nations Sustainable Development Goals is an ongoing work that probably will see it even after I will retire, definitely myself. So I give a horizon of at least 10, if not more years. So what is going on at the moment is that we see that artificial intelligence becomes a new technology asset, both in terms of its resources and its promises. And of course, this will come with its opportunities and challenges. We know the history on short because we are eyewitnessing. This is related to the catalysts in which practically this call is part of, because we are both in an engineering and say technological wave of making use of the Internet of Things, of the big data challenges and opportunities given by the technological breakthroughs, most related to storage and computational powers, doubling continuously every, say, 6 to 18 months to be aligned with the laws we are aware of. And at the same time, with the continuous approach to democratize the environment and the scene of data, but making it, say, public through open science, government access, and similar citizen sciences initiatives. Examples are in this slide. You can see that institutions from Met Office, and not just necessarily in the UK, we're talking about the entire world. A good example is Kenya in Africa. And indeed, the European Commission with its developments related to anything from environment to, say, population or industrial facts. And of course, the United States, that is still reported as being the main contributor, at least within the scientific domain, align practically our technology and our promises to the society, economy, and population, and hopefully to the less personalized but still active actor of the environment, including wildlife, for example. So align their technology developments with still an ongoing, say, series of industrial revolutions. And I'm very, in a way, proud, in a way, interested, in a way, confused to say that we in Bradford are part of these revolutions, at least within the, or actually from the very recorded start with Industry 1.0, when mechanization and steam and water powers, subject of our call today as well, were involved since 1700s, 1850s, 1900s, with the textile industry that has shaped Bradford as a Victorian successful story. But indeed, we can see that these developments continue from the Industrial Revolution 2.0 related to the presence of electrical power, that we can see it coming back with another shape nowadays. Industry 3.0, in which we started seeing at the times of our young university degrees that computers were starting actually playing a game in the early robotic stages. I'm talking about 1970s, 1980s. The smart factory and manufacturing revolutions we're seeing nowadays as Industry 4.0, and the already coming and challenging Industry 5.0. Now, I'll just focus here. I practically wanted to draw your attention to this because while Industry 4.0 is a data-centered revolution, Industry 5.0 is a human-centered revolution. And this is the challenge we are seeing in the Sustainable Development Goals as well. So I'll just jump very quickly now just to allow you to focus into the definition of intelligence, because we still struggle with personalization of artificial intelligence. That is nothing else at this stage but just a technology revolution, not a humanistic approach, though there are question marks into this domain. I won't go now in. And indeed, for Industry 5.0, we can see already sustainability as being one of the pillars of the new industrial revolution, simply because we want to be human-centered. And we can see that the industrial revolutions are to some extent aligned with the history of artificial intelligence. The dates and times, at least for the last three, say, quantified revolutions, 3, 4, 5, 0, are aligned with the developments of artificial intelligence as an active actor in it. I won't go into anything, but just to remind you that humans have forecasted and overseen the need of the responsible artificial intelligence within our domain, and our responsibility itself is a point that is already ongoing research with main keywords of accountability, reliability, ethics, and explainability as part of it, But sustainability starts playing an individual pillar role as well, moving our attention from, say, a responsible artificial intelligence towards a sustainable artificial intelligence. And I'll just make use of some existing published work of colleagues to define that sustainability and resilience as very familiar topics for engineers, for example, will come with the point of meeting the needs of the present without compromising the ability of future generations. And this is where the artificial intelligence as an industrial revolution, no, as previous ones, it will come with damages. So what will be the sustainable artificial intelligence? Within our topic, we have actually a little bit of an equivalence into the terms that needs to go both ways. So we need to define sustainable AI and AI for sustainability as well. Whereas the sustainable AI will include previous responsible ethical points, but at the same time, we need to provide technology to be supportive for sustainable goals. And indeed, the sustainable goals now come.
Professor Neagu, 2 minutes.
Yes, thank you. I'm coming in there. So the sustainable goals that we have listed by the United Nations are heavily actually criticized and reviewed by researchers within their topics of impact to society, economy, and environment. And within this, the artificial intelligence role is measured, for example, in terms of achieving the sustainability development goals with a view of the three main chapters: environment, economy, and society. And you can see that practically based on simply scientific publications, the role of artificial intelligence in achieving the sustainable development goals is still inequitably low, still actually making some progress. You can see the green lights into the different sustainable development goals, particularly related to our agenda. So I just extracted from the paper actually that is listed on top, the presence of artificial intelligence within the water, environment, and health, actually sustainable development goals. And you can see there is still lots of room for improvement. In the environment, we are a little bit better with AI, but many practically topics to still work on the topics related to climate and the use of land as well as the water. Now, indeed, there are different approaches to measure sustainability, and I'll leave here actually the discussion, if any, simply to say that while we're looking at sustainability, we need to look at the governance as well. So maybe in the future, we'll see digital product passports for artificial intelligence technologies as well. Thank you very much. Happy to take questions, if any, or simply to move on.
Many thanks. We'll leave the questions from right at the end. So if you can stop sharing.
I'll need to get back into yes.
So I'll invite now Dr. Cuong and then Professor Rami Qahwaji after Dr. Cuong. Thank you.
Yeah, hello. I'm trying to share my screen. See that one. Share. I hope that you can see my screen now with the presentation. Hello?
Yes, we can see that. Yes.
That's great. Yeah, when I show this, I cannot see the Zoom anymore. So yeah, thank you very much, Professor Iqbal, for inviting me to show my research topic as well as activity in this area about renewable energy system reliability in operation and maintenance. So I'm trying to keep it within the time limit because I know I have about 10 minutes or so, and I just jump right to the introduction. And I would like to start with a figure about our current and future energy system. So the global energy transformation 2050, which is the figure that we can see here. Right now we are 2024, or this figure was taken from IRNI last year. So this is the current, we have a kind of mixed energy diet, I would say, from different source of energy, and you can see here where we are and where we're going to be in 2030, 2040, and 2050. And by 2050, you can see that the global energy will be include a lot of renewable energy, for example, solar and wind, and maybe a bunch of battery storage to supply our need for energy. And so we have a different energy systems or assets in another term, for example, and they are beautiful here. So what do we do with it, and what are the issues with it? That's the message I'm trying to present today. So my first question here is, okay, reliability. What is it, and why reliability? Okay. So if we look at some of the incident in the past, for example, I have a figure here about the blackout incident in North America. So it started in the area you can see in the eastern coast of US. If you know about geographical location, that's the area actually of the state of New York, which city of New York, and also another province in Canada, which is Ontario's, and in the nearby location. And you know that New York and Toronto are the center, the economics or financial center of the world. So if something wrong happened with that, and you can see and can imagine the impact of that incident. So essentially, the problem here was okay. So some issue with the power system over there, and then there's some power cut, and it happened in about 4 days. Okay? So 4 days is huge because there's a lot of the whole world operate based on energy and electricity. Okay? There's an incident related to fires, to traffic issues, there are, financial markets without power. That's very big. There are about 100 deaths directly related to that incident, and also about more than millions of customers was affected by major power disruptions, and the consequence is huge if that kind of incident happened. So right here in the UK, we also have a kind of similar incidents, but the consequence also severe. It started in a wind farm and another power station in the North Sea, and also another power station here. The name is Little Bradford in the middle of the center of the UK. And the incident only happened in about 40 minutes, but there's a severe concern related to transportation delay, power disruptions across England and Wales. So it started from the east of England. It escalated, and the impact, you can see those numbers here. So 500,000 customers affected in that area, and 300 in the other area, and so on. So those are the issues related to reliability, and that's why we need to study the reliability problem. And essentially, if you have a beautiful energy asset, for example, wind turbine, it's not very nice to see it. There's something wrong happened to it, especially in the figure here. So this is very rare incident, but essentially when it happened, it is damaging in terms of reputation. All right. So what do we do here in terms of reliability, operation, and maintenance simulation? Okay, we have a energy asset, renewable energy assets, wind, solar, battery storage, and so on. So what do we do with them in terms of as academics or researcher in the area? We need to somehow find the information related to operations and also evaluate reliability to identify, say, critical component, the availability of the system, the energy production, LCOE, which is the cost of energy, also can help in terms of making a maintenance decision. So what do we do here? Essentially, we do some computer simulations and also do some reliability data analytics based on the information we collect from the system, and we also build computer simulation model for simulate the operation of the system. And then we can do all sort of things, for example, to find which asset or which component within the system are critical, so we can pay more attention to it. And also what kind of say PM is a preventive maintenance action, or condition-based maintenance, or predictive maintenance actions, or recommendation to the system owner to operate and make it more efficient. So some of the example of what we do here in terms of reliability data analysis is, we develop different algorithms to process the data and then analyze and find the reliability information of the system. So this is one of the published work related to wind turbines reliability, depending on different components within the turbine. So those are the components in the turbine. We can find the information related to the failure rates and also the uncertainty, the range of data, data from different sources, and we can relate it to the performance of the system, which I will present in the next slide. So the outcome of those reliability data analysis, we can identify critical sub-assemblies. For example, here we can see the critical sub-assembly in terms of failure rate, which is a term in reliability engineering. Is some name of the subsystem here: electrical pitch, control, blades, and hub. Essentially, this is the rotor or control system. But in terms of downtime failures, we can have other subsystems. For example, the gearbox, which is a very important component within the turbine. The generator, which is the guy who generate electricity for us. Other mechanicals in the rotor as well. So those are the example of how we can apply reliability analysis to identify critical components.
2 minutes, Dr. Dow, 2 minutes left.
Yeah, thank you. So next, after getting the data, we can process the data and develop into so-called the sequential multi-color simulation. For example, here, there's the different blocks within that. For example, reliability modeling, system estimation, energy estimation, and cost estimation as well. So we can have the full picture in terms of reliability in operation and also cost simulation. Finally, we can get into, after simulate the operation of the system, we can get further data related to, say, weather condition, the cost information, also the information related to the activities we need to do to maintain our system. So that in another level, higher level, which is the maintenance optimization here, we can estimate the cost, also the time, the energy output, and also different options in terms of determine maintenance strategy. Another bit is we also develop environmental impact assessment model, and as you see, we look at the whole entire life cycle of the asset from manufacturing, installation, operation, and also decommissioning or recycling. So this is my last slide. So you can a concluding remark about this topic and also my presentation today. So renewable energy will be the major contributor to our future energy landscape, as in the figure presented earlier. So we will see more about the wind, of solar, of batteries, and maybe bio energy, as Dr. Pedro already presented earlier today. And reliability is critical to the system of operation performance and maintenance decision making, as well as economic and environmental impact assessment. In here at the Bradford, we have different stages. For example, first we model and simulate the reliability and operation, and then we evaluate the impact on the system performance and also provide recommendation for maintenance decision making, and finally evaluate the economic and environmental impact assessment. And you know that in the future, new technologies in wind, in solar, in bio, in battery systems will keep evolving, and that will bring further challenges in reliability, O&M, and also other technical challenges. So some other partner and also some of the attendees today, if you work in reliability sector, it's a room for us for further collaborative activities and also further research and industry integration and so on. So with that, I would like to thank everyone for listening to my presentation today. I'm happy to take any question, or maybe now or at the end of the workshop.
Thank you, Dr. Daud. Thank you for your nice presentation. I'd like to invite now Professor Rami Qahwaji and then Dr. Farshid Sefat. You have 10 minutes, Professor Qahwaji.
Thank you. And can you see my screen?
Yes.
Yes, you can see your screen. Perfect.
Let me just... Okay, hi everybody. My name is Rami Qahwaji. I'm Professor of Visual Computing at the University of Bradford, and today I'll talk about the use of environmental monitoring. To be honest, the most of my talk will be just because it's relevant to this session, but we'll be looking at how can we utilize AI and satellites to do a better way of environmental monitoring. So I'll focus on the issue of in the environment. How does it look now with respect to the use of space and satellites data? There'll be two specific case studies for things we did in Bradford, and then my personal view at the end. So if I start with the environment, I know we are limited in time, so I'll try to be as quick as possible. What makes an environment? An environment is the interaction of four basic elements. Living organisms, or biota as we call it. There's the land and soil, water, and many people talk today about the importance of water and the lack of clean water and stuff. But there's also the last and fourth important element is air. Well, with air, I mean lots of things. It's atmosphere, it's the air we breathe, and it also includes the near Earth environment, which means the upper atmosphere where we have lots of satellites right now. So all that makes air and the interaction between these four elements define the environment that we live in. So environmental monitoring is the systematic sampling of air, water, soil, and biota in order to understand what's going on with these four major elements, in order to understand their interaction, in order to understand what's happening pollution-wise, the long-term effects of human activities, in order to model activities, sometimes like water floods, water shortages on the long term, and so on. And we do it for a variety of reasons, mainly because we have major problems in the world today. And the major environmental problems that we have, and some of the speakers did touch on this today, is climate change, or which comes under air pollution. We have ozone depletion. And people have been talking about the ozone layer for a long time now. We have air pollution in certain cities, and we know that some cities in the world are more air polluted than others. We have acid deposition. We have outdoor pollutants. We have also indoor pollutants. Noise itself is a major source of pollution. That was for air. Pollution also applies to water, where we have oil spills, we have heat, we have sediments, we have nutrient overload, toxic chemicals. Waste production is another source of problems. We have solid waste that's being produced. We have hazardous and sometimes nuclear waste. We have biodiversity depletion. People talk about extinct animals right now, habitat being destroyed, or habitat sometimes being degraded. Food supply problems, and I remember at times of Corona, there was lots of talk about food supply problems and overgrazing, farmland loss, overfishing, coastal pollution, soil erosion, loss of biodiversity at different parts of the world, and so on. And so this figure goes back from 2005. And if I may there, I will add another element to this, which is the importance of monitoring natural disasters, with all the types of natural disasters that we can face today: earthquakes, volcanic activities, solar storms, floods, and so on. So every country in the world today suffers from some type of environmental problem. So this kind of provides a generic overview from earthquakes to floods to dissertation. So there are lots of activities, oil spills. A simpler view would be something like this, where this is just focuses on the major environmental issue for some countries. So for Brazil, we know that, for example, it's air pollution. For Russia, it's air pollution and the depletion of natural resources. In certain countries in Europe, in Africa, you can see that there is freshwater shortages. Same with Indonesia. In India, like you have water pollution. Pakistan, freshwater shortage, and so on. So every country in the world today suffers from some form of environmental problem. Why are we having these problems? Because population growth is not controlled. We do not control how we use the resources as well. Poverty puts lots of pressures. Then people have taken the environment for granted, that the cost of resourcing, or just to make things sustainable, we're not included in the economic goods. We're not a factor in the economy. And we don't understand these complex interactions in the environment. It's something that we try to model the environment without taking into account how complex it is. So hence, it's becoming very important now to monitor the environment. And we have three major methods that can help us. We can do ground-based sampling and measurements, where you have you can take samples continuously. You have measuring stations on the surface of Earth, and you can take things. You can model to understand. Or my own passion is to use remote sensing or satellite-based monitoring. And satellite-based monitoring is becoming very popular now, because you can use it to monitor the atmosphere. You can monitor the air quality. You can understand what's happening to climate and model climate change. You can use it for resource management, glaciers and snow, flood and drought management. You can see what's happening to the land use or the land cover, predict weather, whether it's on Earth or space. You can understand the hazards, aviation effects, smart agriculture, the dust storms, and so on. Now, the things that are green is things that we haven't really done research on, but the things that are in maroon kind of color, these are things that we have done some research on it here in Bradford. So now we are continuously observing the Earth from space. The figure that you see here, 3 years ago, we had around 6,000 satellites in orbit. Half of them are working. The figure today stands at around 9,000 satellites in orbit. And that's only in 3 years. Many of them is true that are microsatellites, but having said that, space is becoming very accessible right now, which means we have a variety of tools to measure things. And space is important because everything we do produces some kind of spectrum, electromagnetic waves. The sun is the only source of energy to planet Earth. So the planet receives lots of radiation, light from the sun. Some of this radiation is reflected back to space, like buildings or objects. Sometimes they can emit their own radiation, which can be picked up by satellites. And this can tell us what's happening.
2 minutes left.
Okay, I'll try. Sorry, I got carried away. So we can have lots of resources that can be picked up from space, either emitted by objects or can be reflected back by objects, like, for example, natural resources, loads, land, water, roads, and so on. So space is becoming very important. AI, because we have lots of satellites now, we have lots of data, and AI loves data. Data now is becoming the new oil. So on one side, you have problems, you have lots of you have infrastructure that is around Earth, providing you with lots of data. So AI becomes the natural answer to it. Can we utilize this data to understand what's happening in the environment around us? So I'll just give very quick specific examples for work we have done. I had a student from North Africa. Dust storms is a big problem in North Africa. So he wanted to study, he wanted to be able to predict them, monitor them, model them. So we used satellites, Aqua and Terra. And you can see these are satellite images. And if you look carefully, we published this work, you can understand how the dust storms are moving across the Sahara Desert and where it's going to hit next. It's like monitoring tornadoes from being. Another thing we have done is monitoring the near Earth environment, because this is what we call space weather for solar storms, radiation. Everything we do is affected by what happens in the sun. Solar storms can cause lots of things, from affecting aviation, damaging our electric grid, so you will have no electricity, damaging satellites, damaging oil pipes, and of course, so it became very important to be able to predict these things just by looking at satellite. And this is work we've done with NASA, where we take data directly from satellites, we model it, we understand what's happening, we post predictions, and prediction goes directly to NASA. NASA, they have now a public app which people can download. And this means that the whole journey from a satellite capturing an image to it being modeled and analyzed here in Bradford and the prediction results being published at our website and sent back to NASA, to it being made public on the website, on the app and the website, takes about 10 minutes. And this is from the time the satellite receives the data to the time predictions are generated. So this tells you what you can do with satellites. And finally, I think Earth observation is going to be the future of environment monitoring. We have, and the potential for it is huge. For a variety of every application you can think of, I'm sure there will be an Earth observation remote sensing technology to support it. Thank you.
Thank you very much, Professor Qahwaji. Thank you for your nice presentation. I'd like to invite now Dr. Farshid Sefat, and then we'll have Dr. James Ennis. Thank you.
Okay, thank you so much. I'm just trying to share my screen. Right, can you just let me know if you can see my screen?
Yeah, I can see.
Excellent. Thank you so much.
You've got 10 minutes. Thank you.
10 minutes from now. Great. So good afternoon, everyone. Thank you so much for joining. My name is Farshid Sefat. I'm program leader and associate professor from the University of Bradford in the field of biomedical engineering. Today, I'm going to talk about the importance of clean water in managing bacterial vaginosis. So bacterial vaginosis is the most common vaginal infection in females. And by mistake, 62% of women, they become diagnosed by yeast, which is not yeast and is bacterial vaginosis. So in America, there is a big population of female, 21 million females, they get BV each year, and which is the most, common problem in USA. And if you look at it globally, the global prevalence of bacterial vaginosis by region, we can say in India, 29% is the majority, is a maximum, followed by North America, 27%, and in Europe and Africa, we have 25%, and in Australia and Japan and that area, 24%. So it's very, it's common in many females globally. It's not only for a specific region. So we need to keep in mind BV or bacterial vaginosis is not poorly and not completely result of poor hygiene. It's a bacterial imbalance, but is also, according to the recent research, is related to the problem with the hygiene with the females, and mainly to do with the water. And I will talk about it later on. And female usually compared to male detects more microorganisms a lot faster than male because they have a very large surface area. And in terms of anatomy, if you look at the I mean, this picture, the female's reproductive system, they can detect like bacteria, viruses, microbes, or any germs a lot faster than male. So I was looking at lots of literature. There are different types of water. For example, unprotected water for bathing, which females globally in Africa, in South Asia, in East Asia, Middle East, in America, some part, and they use rainwater, they use pond, they use lake, the seawater for swimming and for washing and for bathing. That cause problem and make absorb these bacteria. Even the protected water for bathing look like tap water going to taking a bath. That's increased significantly in the past few years because germ will accumulate it inside the surface of bath. And for the same reason I mentioned in the previous slide, females, they can absorb germs a lot easier than male. So does it return? Yes. 60% of female who treated, they can return these kind of bacterial vaginosis. And the cost to the NHS globally is 37.7 billion. It was expected in 2024, which we are now. That's a big money. That's a huge money. So the cost of tampon sale globally is about $2.84 billion per year. Again, if we can do something to stop this kind of bacterial vaginosis, we can save a lot of money globally. The first treatment is antibiotic, following by estrogen level, also uncontrolled diabetic people. These are the triggers, triggers which people, if they take antibiotic, if they take estrogen, if they have diabetic, if they have problem with immune system and pH, they get it easier. So the current treatment, usually they for example, they use condom, they use tissues, tampon, and different hygiene for like underwear, clean underwear, and many more things. And there's some remedies, home remedies, which I'm not really interested in that, which is good. We need to follow it, but the proper treatment, it need to be either a medication like antibiotic, usually oral treatment, or vagina cream. And existing product in the market usually is a tampon at the moment, and those pads, some of them, most of them, there is nothing, it's just a plain pad to just protect it. But what we do, our solution is to create and design and fabricate advantage of smart bilayer tampons. So these bilayer tampon provide a drug as well as tampon. So this drug, which is antibacterial drug, will release slowly inside vagina, and females, they get in few days, they get fully treated. So we already designed this one in a proof of concept 2 years ago at the University of Bradford with excellent and unique equipment we have in Bradford, electrospinning, which is unique in the country, and then with a different polymer in the polymer IRC center. And we did some preliminary results, such as degradation test. We look at how brittle is the material and how fast they can absorb by human body. And we look at the fiber diameter, we look at the scanning electron microscope, measure all these fibers. So lots of research already has been done since 2 years ago. For example, degradation study, we look at different solvents, different polymers, to see if we make these pads with these drugs, how long does it take for these drugs to absorb inside female's vagina, and how long does it take for these polymers to break down. It looks like a suture. Once you put suture on your body, sometimes GP or doctor, they ask you to come back to hospital to remove it, and most of the time they said, no, you don't need to come back because it's resorbable and it will absorb by human body. We look at the wettability and how fast these tampons become wet, because wettability and the contact angle is important, because as soon as these tampons become wet by secretion inside vagina, then antibacterial agents start releasing inside the tissue, and the treatment actually starts. Cytotoxicity, we look at if these polymers and the solvent we are using are toxic to human body or no. And the good news, yes, there's no toxicity to human body. We work with the pharmacy as well as life science in parallel to detect and measure. 2 minutes, no problem. To measure the release of drugs inside the vagina. So we got some data, but we are carrying on the experiment because we need to be more accurate. So this is our team from Bradford University with Professor Anand from pharmacy, Professor Julie Thornton from life science, and people from Virostatic, which they are our industrial partner. And finally, thank you to my PhD student Elzari, who we got a fully funded BBSRC, and she's working at this project at the moment. And thank you so much for your time. And that's from me. Thank you.
Thank you, Dr. Sefat. Thank you for your nice presentation. I'd like to invite now Dr. Rob Innes and then our final speaker, Dr. Juhana Jaafar.
Thank you, Iqbal. I'm just looking to share my screen now.
We've got 10 minutes. Thank you.
Okay, hopefully you can see that.
Yeah, can see the slides. Yeah.
Okay, great. So I'm going to be talking today on tire recycling and engineering solutions. I'd like to thank a number of colleagues from the University of Bradford, and this was part of a joint partnership project which was done with the University of Manchester, their National Electron Paramagnetic Resonance Facility, as well as the CSIC in Madrid as well. So I'll basically introduce what rubber recycling is and why it's so difficult, and then what our approach is in terms of actually using engineering to recycle tires, and how we characterize the recyclates so that we can then reproduce them into tire-like materials. So tires are a global challenge. There's 1.5 billion waste tires produced every year. And what we're really aiming to do is recycle tires back into tires. At the moment, tires, when they're recycled, get used for lots of different applications, but they essentially are low value applications. You can use them as filler in lots of materials like concrete and asphalt and other kinds of plastics, but the value of those recycled tires is hundreds of pounds per ton compared with the thousands of pounds per ton for a tire-like material. So the aim here is to recycle tires into tires, and by doing that, we're going to be reducing the cost of the tire, reducing the CO2 impact of the tire, and preventing any of the negative consequences of waste tires that can occur, which is landfilling, it's burning, it's pollution. To be able to do that requires quite a lot of chemistry, engineering, material science understanding, because you have to understand each stage of the process. So the ideal goal really is to match the properties of a virgin tire, a tire that has not been through any use and is equivalent to a new product. And a few of the challenges that you need to take on when trying to do that is avoiding oxygen uptake, which is a problem when you recycle these kinds of materials. Generally, they absorb oxygen from the atmosphere. You want to avoid contaminants, which can happen in recycling facilities. So you tend to get quite a lot of metal contaminants. And then you, of course, have to match the chemistry and structure of the starting material so that the properties are the same, because you don't want the recycled material to have lower mechanical and dynamic properties than a non-recycled version. So why is recycling rubber more difficult than other materials? Well, essentially for most materials, metals and plastics I'm referring to, you simply have to separate them and melt them, and the quality of the material is essentially determined by the quality of your separation and your mechanical and thermal melting process. Tires and rubber materials don't melt if you heat them up. They burn. So the first thing you have to do is undo all of the clever chemistry that was introduced to make the tire-like material in the first place. And what that is it's removing sulfur crosslinks. So in this case, this is what rubber essentially looks like. You have these long carbon chains, and natural rubber is a cis isoprene. And then to make them into the sort of flexible material that you know with its good thermal properties, you have to introduce these sulfur chemical crosslinks. So in order to recycle them, you have to remove the sulfur crosslinks selectively. If you were to just break bonds randomly, then what happens is you're shortening your carbon chain and you affect the material properties. So you have to have a means of breaking the sulfur bonds without breaking the carbon bonds. And that's the challenge. And it's something that, you know, for the past few decades, we've not been particularly good at. But now the technology is advancing, and over the last 10 years, there are some really good examples of how you can selectively break sulfur bonds without breaking the carbon chain. So that means you can then maintain the molecular weight of the polymer, which means that you get good mechanical properties when you recycle it. Our approach uses a technology that was developed by Sichuan University. It's known as solid-state shear milling. It's a mechanochemical process. We don't actually introduce any chemicals, but we're using the mechanical shearing essentially to fracture selectively the sulfur bonds. So what it is it's two metal plates with these surface structured grooves. So these are steel plates, and one is spun at high RPM. They are forced together, the material is fed through, and depending on the feed rate and how fast you spin the plates, you can control the recycling of rubber materials and other materials. So this has also been applied to plastics, but this particular approach focuses on tires because of the global challenge. Then to be able to understand the network structure of rubber, there's quite a few tests that you have to do. If you don't understand the structure of the starting material, you don't understand the structure of the recycler, then you can't hope to reprocess it into a material which is tire-like. So there's a lot of characterization that has to be done to make the process work. And then once the process is optimized, then the hope is that we wouldn't have to characterize individual tires. So at the moment, you need to use swelling measurements to look at crosslink density, which is the number of sulfur crosslinks. You need to look at the length of those sulfur crosslinks because they can be mono, di, or polysulfidic, because you introduce sulfur as an 8-membered ring. So the polysulfidic crosslinks can be quite long. That, of course, enhances flexibility, but it reduces thermal stability. You have to look at the network defects. So as you're breaking the material down, what actually happens to the structure of the polymer chains that remain? You have to look at the average crosslink structure. So once you start breaking them down, which of the crosslinks have you broken? How long are your polymer networks now? And you have to look at, when you break a sulfur bond, what you basically do is you generate two chemical radicals, two sulfur radicals, or a sulfur and a carbon radical. You need to be able to measure those so that you can understand what happens to them during reprocessing. So there is something known as the Horrocks plot, and this basically tells you whether you are selectively breaking the sulfur bonds, which is what we want to do, or whether you're breaking any bonds, which would include the carbon bonds, which is known as reclaim. So that's what we're trying to avoid. So if you look at the graphs here, the blue line shows you this random scission, which is what we don't want. The green line shows you the perfectly selective scission, which is what we do want. And what we're hoping to do essentially is follow the green line. Now, if you look at the one on the left, our initial sol fraction is a little bit high. That's just to do with the way that the tires were made. But once you remove that, once you account for the starting high sol fraction, then you actually find that the process that we're doing does appear to selectively break the sulfur links. So our initial step wasn't very successful, but the subsequent steps for the red and black dots here show that we're actually doing quite a good job of following this sulfur cross-link scission line. And we've got more data to back that up, but unfortunately I don't have time to present everything. So what happens when we put it through the S3M process is we start off with a granulated material that is about 5 mil in size. So the tire...
You have got 2 minutes, Rob. 2 minutes.
Thank you. So the tire has to be basically shredded. It has to have the metal wires removed. It's then granulated. All of these are already standard industrial processes that have been well developed. We then take it as a 5 mil granulate and we further break it down to a powder of typically around 100 to 300 microns in size. As we do that, the cross-link density reduces, which is good. And if you look at the sulfur bonds that we're breaking, it's more selective for the longer sulfur cross-links. That means that we need to think about that when we reintroduce cross-links, because ultimately to make the tire again, we have to reintroduce these cross-links after having broken them. So now we need to focus on reintroducing the longer cross-links because those are the ones that are more selectively broken by the process. So this gives you a sort of example of what the change in the chemistry looks like as you do the mechanical devulcanization. So we've got these long chains of cis-isoprene with these sulfur cross-links of various length. We then produce these radicals, which are drawn by these yellow dots. The filler in there is basically unaffected. The polymer chains are designed to be unaffected. So then we need to recross-link these yellow dots that have been created using the chemical radicals. Around 30% of the cross-links remain, but that hasn't affected the processing too much, which is good. It just means that we then need to modify the cure package. And work that we have demonstrated recently, so sorry, here in red, we have the original material, so the original properties. We did 9 different formulations to try and look at, you know, if it was going to be affected by cure package, filler, all sorts of things. And we found that basically if we considered all of the chemistry, if we modified the cure package, then essentially we could, the black is then recycled, we could match the properties. So we could match the tensile strength, we could match the elongation at break using 35% recycler. And this is a world leading result. So nobody's managed to match the tensile strength and elongation at break as well as we have here. This is a recent result, it's not yet published. So we're really looking forward to sharing that with everyone. So conclusions is that basically tire recycling is feasible. It just currently requires a lot of characterization. But moving forward, we're going to create a process that will understand all of that and mean that you don't have to do that for each individual tire. And we'll start to look at post-consumer materials and the limitations of recycler content. Thank you for your attention.
Thank you very much, Dr. Prince. Thank you for your nice presentation. So we move to our last presentation by Dr. Jaafar from Malaysia. Juhana, if you can share your screen.
Yeah, okay, sure. Thank you, Dr. Iqbal.
Thank you. Looks like we are frozen. Juhana, can you hear us? Saffron, can you please unshare the screen and let her do it again? It looks like it's looks like it's frozen.
There we go.
Okay. Juhana, do you want to try again?
It might be that her Zoom's frozen too. She might not be able to hear us.
Yeah, because she mentioned that internet access is poor.
Maybe Professor Iqbal, maybe you could ask some questions to the panel, and if Juhana can rejoin, then she can complete her presentation.
I think that will be a good idea. Right. So while Dr. Jaafar is trying to sort of connect us, let us start the question and answer session to the panel member. Panel members, you can ask each other question as well, or some. We have got some attendees. We started with about 11, now down to 6. So from the attendees, anyone want to ask any question? You can type in the chat box if you don't want to speak. Any question from the attendee? Right. Any question from the panel members to other speakers? Right. Maybe I can start some question. Thank you again, all the speakers, for your very nice presentation. I'd like to request that if you can share your presentation in sort of PDF format and send to Dennis, for sharing between us, and if any attendees request later on, if that can be shared. Thank you. So I have got few questions for few speakers, but I will start with Professor Qahwaji. Mentioned about smart agriculture. So can you please tell us, how that can help us to reduce the amount of water needed for agriculture? As you know, in my presentation, I mentioned that 70 to 80% water goes in agricultural use for irrigation and other purpose.
So, I'll be honest. So smart agriculture is the term that we use when you use new technologies to monitor things like the quality of soil, the quality of plants, vegetation, and so on. And satellites, they are used recently to monitor the health of the crops. Because what satellites do is they measure the electromagnetic radiation coming out from the Earth's surface. And as you have different stages of crops growing, the level of chlorophyll and vegetation changes in them, which means the emission that's coming out of the crops keeps on changing. So this is one side we do for smart agriculture. The other thing we do is there are very good tools used for modeling the water levels, things like floods, things like natural disasters occurring because of them. So it might not help us directly to reduce the dependency of agricultural use on water, but it certainly will help us in increasing the things like the productivity of the current crops that we have, monitoring any signs of disease, and ensuring that we have the optimum use of water levels available for us, and of course mitigate any effects from floods or natural disasters that could affect the productivity of the crops that we have.
Thank you. Thank you. I think we'll have opportunity to talk further. You and me were at the same level. I think I have got some interest in that, definitely. Any question from other panel members to any other speakers? Right. Okay. I will carry on. Right. To Dr. Farshid Sefat, right? It's a very interesting. I never knew that, unclean water can create such a big problem and costly problem for health service. Do you have any clue that which toxic components in the sort of wastewater or unclean water triggers that problem in women? Because there are plenty of toxic elements there in unclean water, right? So is there any particular one which is dominating kind of thing, which, the wastewater treatment people, should taken care of or do some work together?
Thank you, Professor Iqbal. Yes, we have lots of, microorganism can, attack human body, especially female. In this case, which is bacteria, different type of bacteria can attack human body, like a gram-positive, gram-negative, and there is a big list of bacteria. It's not only one or two, there's a big list. And so for that reason, GP or specialists, once they want to treat it, they need to identify which type of bacteria is that, and then they can prescribe a relevant antibiotic. The problem with antibiotic, sometimes women become resistant to this antibiotic, and that's why the bacteria vaginosis, which we know as a BV, just come back to the females. And it doesn't matter, are you from a poor country or rich country or developed country, so it can happen to any females. Because as you saw from my slides, there are some unprotected water or some protected water. So it covers for rich and poor country as
well. How do you educate the women about this issue they're aware of? Because this is the first time, to be honest, I'm hearing this problem related to unclean water. Seriously.
Yeah.
What will be the roles of social scientists and others, to make it, make the women aware of this global issue? And I sincerely, I did not have any idea.
I believe, honestly, I believe we need to have a very large public awareness for females globally. Not, as I said, not only for poor people, even for rich people or for middle class people, anyone, to understand when they keep in touch with contact with water, they need to make sure there is something inside water. If it's not clean, they can harm them. So if they take bath inside their house, even in everybody's house, we have bath, and then if that bathroom not cleaned with proper chemicals and wash and rinse properly, then we are in the risk of getting this. So we need a proper public awareness for everyone in the UK and every country. For those people who are in a developing country and poor countries, I think that's a bit more challenging, but that can be done by, again, public awareness and going to the villages, going to the cities, talk to them and let them understand from the basic information what's happened to you. I used to live in different countries, like I used to live in America, I would teach there. I used to live in Saudi Arabia and some Asian country, and I saw some females, they have a very low knowledge. And then once we teach them in a very basic language, you need to follow this instruction to protect your body, they listen, and then lots of problems will solve. So it's, globally, we need to do a big effort and let everybody know.
Excellent, excellent.
You are muted, Professor Iqbal.
Sorry, Dr. Arrillaga, you want to ask a question? Thank you.
Yeah, it was a question on different topics. First, congratulate everyone, because I think I've learned that there's lots of room for collaboration. Well, I think my question lands in the introductory presentation of Professor Mujtaba, actually, because I read the same news about the microplastics, and I found it terrifying in a way, because they were speaking about potential cardiac problems that can derive from the presence of microplastics in water. And I've been thinking for a while, no, because there is a big problem on how to deal with microplastics. And in my present research, using water for processing and obtaining value-added products, one of the main ideas is trying to use not fresh water, but contaminated water. And thinking about the presence of microplastics, at least in the context of my research, I would be thinking of a very good feedstock in order to get good value-added products from microplastics. So I don't know if you have any further views on what can be done in terms of dealing with that.
What I have seen, there are a number of call, the funding call about dealing with microplastic, because it is not only a problem here, a problem for even the desalination industries, dependent on the seawater. So the intake of the seawater, they have got microplastics in it, and then treating them, of course, becoming difficult in how you remove it. Otherwise, it can do the fouling of the membranes and many other things. The same goes with the wastewater. Also, not only seawater, wastewater has got also considerable amount of microplastics. So I did not know about until about a year ago. I have started, looking into it in more detail. But yes, any sort of collaboration would be fantastic in that area. Thank you. Right. Good. Before you go, I want to ask you a question about the liquefaction of organic waste, right? So when you do the liquefaction of organic waste, what is the percentage, the kind of the overall conversion?
Okay, now I'm unmuted. The overall conversion is very high. We can consider, it's difficult to talk about the conversion in the typical way, because in the end, you start with a biomass or an organic waste that has certain characteristics, and we can talk even of 100% conversion if we consider that even the solid fraction has different properties at the end of the process. But it's very difficult to say. If we talk about conversion to products that are not solid, then we are around 70%, because we are recovering 30% solids, 35% solids. And those solids, is worth saying that we denominate them biochars, and these biochars already have for example, greater energy content than the original biomass.
I see.
So yeah.
Right. Okay. Good. Thank you. Dr. Jaafar, are you ready? Can you hear us? Will you be able to make your presentation now? Will you be able to connect? Right. Maybe she is still having a problem. Right. Again, any question for other panel members? Any question to anybody? Okay. Dr. Rob Ennis, to you about this rubber recycle, right? You mentioned about virgin rubber, and then you want to convert tire to tire. My question is how many times a tire can be recycled to make again a tire without losing much of the mechanical or other properties, kind of thing? How many times you think? Is there any life cycle analysis, or you can trace it in a particular tire that where it ended up, or what is the mechanism of following that up to find out exactly what's happening?
Yeah, thank you. It's a very difficult question, because up until recently, the answer to how many times can you recycle a tire into tire and get the same properties was zero. All of the previous efforts to recycle tires basically resulted in reduced properties.
Yeah.
So this really is the first example where we've basically got exactly the same properties, and it required using idealized tire type materials. In theory, the main issue is that normally you break the molecular weight of the polymer chain, and that's you're breaking the carbon bonds. You're not being perfectly selective for the sulfur bonds. In theory, if you can perfectly break the sulfur bonds every single time, then the answer is as many times as you want, like with recycling, say, aluminium or something else. The reality is that that's going to be probably too difficult. So I would say a realistic target might be twice or three times. One of the big problems that you've got, though, is tracking it. Once you put a recycler back into a tire, then you have to characterize that again at the end. So I can envisage there being some clever AI technology, probably based on blockchain, where you would track the contents of tires. It's going to require input from manufacturers, so it's quite a complex issue, but at the moment the research is only just getting to the solutions.
Yeah, I can see that 24 years ago, we did some work on, recycling of plastic can, the jerry can for milk bottles and kind of thing. And we did some investigation back in Bangladesh and India, and we looked at the recycling. We are tracking all those materials put into recycle again, looking at the properties, melting flow, the mechanical strength, and et cetera, et cetera. And we did some modeling also, and which was showing that, yes, without losing much of the properties, you can recycle about 4 or 5 times before you have to make a different product completely, not the original one what you wanted to do. I will share that paper with you, which was published in Waste Management Journal, and people are looking into it as part of the circular economy kind of thing recently. I'll share that with you, just to have a look. Maybe a very similar thing can be done for tire recycling. Right, any other question? We have got 5 minutes left.
There is a question in the chat, Professor Iqbal, from one of the attendees.
Right, let me have a look. Do you know where is this question is? Will you be able to read that question? I cannot see that, unfortunately.
Yep, of course I am. It's from Barasa, and it says, Professor Farshid, I'm interested in your area. How can I get in touch? I'm in Africa, brackets Kenya. However, your presentation wowed my thinking.
Thank you. Dr. Farshid, can you put your email address for everybody on the chat box so that
I do that. No problem at all.
So gentlemen can contact you. And as I told you, I have got a lot of interest in that as well. But if you can share your email address.
I'm going to do it now. No problem.
Thank you. And do it for everybody. Right. Any other question? I can see Dennis, your hand is up.
Yes, I just wanted to say, Dr. Iqbal, if possible, could we try to speak with Juhana once more? She's just messaged me to say that she would like to try again.
Yeah, okay. Juhana, are you ready? Do you want to share?
Yes. Actually, I finished my presentation just now, but then when I returned, then the session already finished. I don't know. My internet is very bad, I think. I'm so sorry about that. So are you allowing me to present my work?
Yes, please, if you can. We'll wait for that.
Yes,
please,
thank you.
If you can share. Thank you.
Yes.
Yes, we can see that now.
Okay.
Yeah, so you've got 10 minutes, please. Thank you.
Okay, thank you so much, Prof. Iqbal and all for this opportunity. So my name is Juhana Jaafar. So I'm from Advanced Membrane Technology Research Center. I'm Tech UTM, Universiti Teknologi Malaysia. So today I would like to share with you about this topic, photocatalytic membrane for wastewater treatment. So as for the introduction, this is the facts about water. So generally speaking, 70% of the Earth's surface is covered by water, and out of the 70%, only 3% are fresh water. And from these 3%, unfortunately, 70% are in glaciers form and 20% are groundwater. So only 1% of the water is drinkable water. And the worsening scenario is that many countries are high in water stress due to the clean water shortage that are caused by the population growth, industrialization, and expansion of irrigated agriculture. So here I would like to highlight the potential solution from the tertiary treatment approach, such as we have the membrane technology and also the advanced oxidation process like photocatalytic process. And the innovation solution from these two treatments can be the hybridizing of these two technology that can simultaneously filter and degrade the unwanted pollutant. So talking about the conventional membranes such as microfiltration membrane, ultrafiltration membrane, nanofiltration, and also reverse osmosis that are driven by pressure and also pore size, therefore fouling issue is inevitable in membrane separation process. Therefore, hybrid photocatalytic membrane technology become a promising solution whereby the immobilized photocatalyst can help to degrade the fouling on the membrane surface or sometimes in the membrane pores, and hence this hybrid membrane can have a self-cleaning feature. Okay, so here I share with you one of our study on the blended photocatalytic membrane. We make translucent photocatalytic membrane for OPW treatment. OPW means oil field produced water. So in this study, we use PVDF as the polymer base due to its high chemical and mechanical stability. So in typical, actually, PVDF blended photocatalytic membrane, light penetration onto the immobilized photocatalyst is inhibited by the opaque membrane surface. So this initiates us to fabricate the translucent PVDF membrane. Okay, and this is how we make our membrane. Okay, the hollow fiber membrane, translucent. So we start with the preparation of dope solution, consists of the PVDF as the polymer, DMAC as the solvent, GCN as the photocatalyst, and then we have PVP as the pore former, and also we have the LSMM, the hydrophilic surface modifying micromolecules as the additive. Okay, and in this in this video, it shows how we fabricate our membrane using the spinning machine technique. Okay, this is our setup. Okay, and here you can see in this reservoir content of our dope solution, and it is coming out from this spinneret and goes into this coagulation bath. Normally we use room temperature water as the coagulant, but to make it translucent, okay, we use ice bath, okay, for rapid cooling and make it into translucent form, okay. And then we collect it at the end of this machine. We have drum here, okay, and in order to make sure it is sustain its translucency, okay, we place it into the airtight bag and place it in a freezer at 0 degrees C for 1 week, and then followed by drying in an oven for 60 degrees C for 12 hours. And you can see here, this is the photo of our membrane. It is translucent, and most of our membrane, we managed to get about 85-87% of translucency. Okay. And this is the image of our surface and a cross-section morphology of our membrane. So you can see there are variations of morphology from the parent translucent PVDF. We have the addition of PVP, varies the graphitic carbon nitrate catalyst loading, and varies the LSMM. Okay, and also we compare with the opaque PVDF membrane. Okay, here. And as you can see, the addition of the GCN has shown a disrupted structure due to the instability water intrusion that was further developed by the non-homogeneous distribution of the hydrophilic GCN. Okay, and then interestingly, when we add the LSMM, you can see a well constructed structure of the membrane was obtained that is similar to the opaque membrane. So this is because the LSMM that has the tendency to attach with the GCN has assist to concentrate the GCN to the membrane surface, and this reduce the pore size and contribute to a more porous membrane surface, and this will inhibit the water intrusion, and we can get a well-structured membrane morphology. Okay, in order to assess the performance of the photocatalytic membrane, we carry out the permeate flux under hybrid condition. So there is no improvement, if you can see, when the for the permeate flux for without and with the light irradiation for the membrane without the GCN photocatalyst. Okay, but when the light is on, which means the photocatalytic process is operating, so all the membranes with the catalyst showed significant increase in permeate flux. So this shows that the in situ photocatalytic degradation of the oil molecules occurred during the filtration, and thus reduce the tendency of fouling and consequently increase the permeate flux. Okay, and the removal of oil molecule from the OPW also been conducted under hybrid condition testing, and the membrane with the GCN catalyst and LSMM has shown high removal of pollutant, as you can see. Okay, and you also can see a significant reduce of the organic species peaks after the treatment using our membrane. And also here you can see the brownish color of our initial OPW that we synthetically prepared at 1000 ppm has turned into colorless solution after the treatment. And we also conduct the regeneration test to observe the self-cleaning effect on the photocatalytic membrane, whereby if you can see, obviously all the tested membrane have oil particles attached on the membrane surface. However, as expected, the membrane with the GCN catalyst and LSMM show very less attachment of oil particles. And we also conduct this, observe our membrane after the test, and with the good formulation of the materials in the membrane, you can see very less observation of oil particles in the membrane after the test. And we also observe the translucency after the testing, and you can see the reduction of the translucency, very few, less than 10%. And for the future outlook, we are studying about the day-night photocatalytic membrane, whereby the semiconductor photocatalyst is paired with energy storage materials such as vanadium oxide, MXene, GCN, and etc.
You've got 2 minutes.
Thank you. All right. Okay. So this diagrams actually shows the mechanism of the day-night photocatalytic membrane through the charging and then discharging, discharging like a reaction, where the catalyst will absorb the light and the energy storage material will store the electrons. And at the same time, the photo degradation works simultaneously by the photocatalyst. And then at night, or without any light source, the energy storage material will discharge the stored electrons and react with the substrate like wastewater, for example, to produce the radicals, and degradation will continuously occur. And this could prevent the light dependency on the photocatalysis process. Okay, so that's all, Prof. Iqbal. Thank you.
Thank you very much, Dr. Jaafar. Right, with that, we would like to conclude the session today. I'd like to thank all our speakers for their time and effort they have made. Unfortunately, we'll not be able to take any more questions because several of us have got other commitments. I'd like to thank Denise and Saffron for taking care of us and so that we could run the program smoothly. And I would like to thank our attendees who have joined from different parts of the world.